This video covers Pre-Calc Notes 9.5. We're going to be talking about the Binomial Theorem and how we use that. Basically what the Binomial Theorem is a shortcut for us to be able to take a binomial and expand it without having to continuously FOIL it. For example, if I have something like this, 2x plus 5, and I ask you to raise it to the 12th power. You don't want to have to write this out as 2x plus 5 times 2x plus 5 times 2x plus 5 and do that 12 times, okay? And then FOIL, multiply those two together, get an answer, multiply that by the next binomial, multiply that by the next binomial, and so on. So this theorem is a shortcut so we don't have to FOIL 12 times. And before I actually show you how you would deal with this type of problem, I want you to look at a couple examples because basically the binomial theorem is understanding a pattern or the relationship that's occurring as we move from term to term. So here are the 7 different rules that are associated with using this binomial theorem, and I want to go over them by looking at this example here. If you're taking the binomial x to the first, raising it to the first power, sorry, x plus y to the first, versus x plus y to the second, x plus y to the third, to the fourth, and to the fifth. Notice that there's a pattern that's occurring with each of these answers. So the first thing you should recognize is that the number of terms in the expansion is 1 more than the exponent. So when there was an exponent of 1, you've got 2 terms. When there's an exponent of 2, you have 1, 2, 3 terms. When there's 3, there's 4 terms. So that tells us how many blanks we should actually draw on our paper to be able to solve this problem. And that's how we're going to start all of these problems. So with this one, I'd want to give myself 13 blanks. The second thing, it says the first term in the expansion is always the first term in the binomial raised to the exponent. So notice that in my expansion here, when it was x to the first power, it's just an x to the first power. When it was x plus y squared, the first term was an x squared. This one would be x to the third, x to the fourth, x to the fifth. So for this one, it would have been a 2x raised to the 12th power. So it's always the first term of the binomial raised to whatever the power is. The next term in the expansion has 1 less exponent, so the exponents will decrease as we go over. So notice that with the x. It starts off as a 2, the next one is a 1, then there's 0 x's. If we look at maybe this one down here where we have a few more terms so we can see the pattern, the x term starts off with a 5, then the x term here has a 4, then a 3, then a 2, then a 1, and then there are no more x's. So we start off with the highest exponent for the first term and we work our way down to 0. On the other hand, the next step here says the exponents increase on the second term of the binomial. So if we're looking at the y values, notice that you have no y's in the first term, but my second term will have 1 y, then 2 y's, 3 y's, 4 y's, and 5 y's. So whatever this term is, we start off with the highest exponent, we'll work our way down. This term starts off with none in the first term, and then it builds its way all the way up to 5. The fifth pattern here is that all of the exponents per term add up to the original exponent. For example, if we're looking at this one, the x plus y to the fifth. The original exponent is 5. This term has exponents that add up to 5. This term has exponents. 4 plus 1 is 5. 3 plus 2 is 5. 2 plus 3 is 5. 1 plus 4 is 5. 5 by itself. So all the exponents will add up to be whatever these are. So again, let's just verify that with this one. All the exponents should add to be 3. 3, 2 plus 1, 3, 1 plus 2, 3, and then just a 3 there. Number 6, if the leading coefficient is 1, the next coefficient is the same as the original exponent. So if we look at this, start with this one. If the leading coefficient is 1, and that's what this is in this problem here, the leading coefficient is a 1, then the next one has a 3, then the next one has a 3, and the next one has a 1. We're going to talk a little bit more about how to get those coefficients by using Pascal's triangle. I think that's going to be an easier method for us to figure out how to get these coefficients that are with each of the terms. And that's something we'll talk about a little bit further down in the notes. So the leading coefficient can be found with Pascal's triangle or using combinations, which again, that's something we'll talk about as we progress through this section. But those are basically the 7 different rules, and number 7 again is dealing with the coefficients. So again, we'll get to that as we progress through. But those are basically the 7 different rules to expanding the binomial. It looks really complicated, but once you've established the pattern, it's pretty easy to expand these binomials. So let's talk a little bit about finding the exponents associated with our, the coefficients associated with our terms. So one of the ways that you can actually find the coefficients is by using the binomial theorem here. In other words, the rules for combinations, NCR. And again, this is something that is in your calculator. This is under the math button on the graphing calculator, and then go to probability across the top, and then you should see this NCR button. And I'll show you how to use that in just a minute here. If I wanted you to find the coefficient of the x to the 7th, y to the 5th, I'm asking you to find the number that is out here in front. Now the way that you're going to do that is you're going to use this binomial theorem, or you can use Pascal's triangle, and again I'll show you that when we get to another example. But the binomial theorem will say this: if it's n terms c taken r at a time, in this problem we're dealing with an exponent of 12, so it would be 12, then combinations of either one of these exponents. You can use the 7 or the 5. So 7, or you can do it as 12c5. It doesn't matter. You're going to get the same answer for either of those. So if I do, let's take the 12c5 and expand it out using the formula. The formula says do n, which is 12 factorial, over 12 minus 5 factorial times 5 factorial. Because remember, this would be my n, this would be my r. So this would be 12 factorial over 7 factorial, 5 factorial. And 12 factorial would be 12 times 11 times 10 times 9 times 8 times 7 factorial, so that those could cancel out, and then you still have 5 factorial, 5 times 4 times 3 times 2 times 1. Multiply your numerators out, you get 95,040. Multiply your denominators out, you get 120. Divide that, you get 792. So 792 would be the coefficient that I would put in front of here. So my answer is really to this problem is 792. A much easier way of doing that is to go to your calculator and type this in. So you're going to first, you have to type in the n value, so you do 12. Then type in, or hit this button, the NCR button, which again can be found under math, then probability, and then type in the 5, and you should get 792. Just to verify that these are both the same, type in this 12 NCR 7, you should also get 792. And so again, this is how you can find your coefficient. You take the exponent that you're dealing with in your binomial, which in this case was 12, and then you take either one of the exponents with each of the terms here, and you use combinations. So to make sure that you understand how to use your probability button in the calculator, your combination button in the calculator, I want you to pause the video and do these 4 examples, and then I want you to play the video and see if you're getting the same answers as I do. So these should be the answers that you get when you use the button in your calculator. You should get 28 and 28 for both of these, and 120 for both of these. Again, the reason for why you're getting the same numbers is that both of these add up to be 8, and that's what you were taking out to the front here. And then both of these numbers here add up to be 7. So, I'm sorry, add up to be 10, and that's the number that you're taking out to the front here. Just like this example that we did, where I said that both of these should equal 792 because 5 plus 7 adds to be 12. That's why you're getting the same values for these. So again, one of the ways you can find the coefficients is by using combinations. Let's talk about the other way you can find the coefficients. The other way that you can find the coefficients is by using Pascal's triangle. And so Pascal's triangle looks like this. You start off by putting a 1 in the top of the column, and then each row, each number that is on the edge of the column would always be a 1. So all of these would be a 1. Each number along the edge would always be a 1. Then to get any of the additional numbers, what you do is you add up the numbers that the boxes are touching. So example, this box here is touching this box and this box. 1 plus 1 is 2. This box here is touching this box and this box, so that gives me 3. This box is 1 and 2, so again 3. This box would be 3 and 1, so 4. This box would be 6. This box would be 4, 5, 10, 10, 5, 6, 15, 20, 15, and 6. And so this is Pascal's triangle, and you can continue to make Pascal's triangle larger and larger. You'll notice that each time you just add one more box, so it's one row, it's 1 term, 2 terms, 3 terms, 4, 5, 6, and so on. Alright, so how do you use this to help you get the coefficients? So go back to one of the examples we talked about at the very beginning. If I asked you to find the coefficients of x plus y raised to the 5th for each term, notice that there's 1, 2, 3, 4, 5, 6. There's 6 terms, because that's 1 more than the exponent. You would want to go to the row that has 6 terms in it. So 1, 2, 3, 4, 5, 6. That would be this row right here. So the 6th row would have 6 terms in it. And notice that all the coefficients would be 1, 5, 10, 10, 5, and 1. 1, 5, 10, 10, 5, and 1. Notice that they match up. So you can use the row of Pascal's triangle for however many terms you have. You've got 6 terms, you need to use the 6th row. If you had 12 terms, you have to use the 12th row to find those coefficients. And that's going to be a shortcut in solving these problems, is to be able to use Pascal's triangle to be able to do this.